let's do this. Floor this and do 2.0. So this is normal. You know, it didn't compute it precisely, but that's fine. So that's about a quintillion. 999 quadrillion is almost a quintillion. Now let's look at what happens if we do about 1.58. What do we get? Well, this is only 165 trillion. So we went from a quintillion to a trillion with Karatsuba. That is much fewer operations than we'd have to compute otherwise. However, that's still a lot. 1 trillion arithmetic operations for 2 billion digits. It's actually 165 trillion. That's still a few orders of magnitude off. So there's an even better way to multiply when your numbers are gigantic. And that's called a method of using fast Fourier transforms. The way fast Fourier transforms work, I won't get into deeply right now, maybe in another thing. But the idea is that we can actually have n times log n. So n log n of n, which is times n log n base 2. So instead of a trillion, we now have n log n of a million, which gives us 29 billion. That's amazing. For a billion digits, we only have to do about 29 times that to do a multiplication. So again, in the most case, just to remind you, we had 1 quintillion operations. That's way too many for a single multiplication of 2 very large numbers. With Karatsuba, that brings us down to about 150 trillion. That's not bad, but it's still many orders of magnitude. But then when we do fast Fourier multiplication, I'll write that out. That is fast Fourier, without the R pronounced, fast Fourier multiplication, we get 29 billion. That is just incredibly better. N times log n is almost linear. It's not linear, but it's just so close. Log grows so slowly, being the inverse of a function that grows really fast, that we almost get linear scaling with our digits. So the approach I would like to use is do big multiplications using fast Fourier transforms. But we run into another problem. 2 problems, actually. The first problem is fast Fourier transforms use floating point arithmetic. And when you do floating point arithmetic with very large numbers, you get round-off errors. Now, when your numbers are in the millions or so, the round-off errors aren't so bad. In fact, it's provable that the error bounds are small enough that when you do 2 multi-precision multiplications, you get the correct answer. However, when you get into very large numbers, like billions of digits, you actually lose precision. You lose precision, and as such, a few of your digits, or maybe all of your digits in your multiplied result are incorrect. So that's kind of a damper. Fast Fourier transforms to, we can go look up a Fourier transform real quick. Fourier transform. If we look at a Fourier transform, the implementation of it, the main idea is that we do a bunch of multiplications by these terms, e to the power of 2 times pi times I times some other stuff, which would result in a complex floating point number. So Fourier transforms typically operate on real numbers or complex numbers, and they give floating point results back. So the question is, what can we do to make this not susceptible to round-off error? We might be able to do some numerical analysis and break our computations in such a way that we can bound the error in a particular way and so on. But that, in my opinion, is pretty hard. Instead, if we look at the mathematical structure of a Fourier transform, you might notice that e to the power of 2 pi I with some multiplied by some integer is a root of unity, a primitive root of unity, which means that if we multiply this or take these things, and they basically, if you plot these in the complex plane, they will all have a distance of 1 from the origin, from 0. And so they all lie on the unit circle. Furthermore, all of these points separated, once you go from 0 to t with this parameter n right here, we will step in this unit circle in equal steps, forming a regular polygon. So if we have a primitive root of unity such that the primitive root to the power of some integer equals 1, then perhaps we can choose a different kind of primitive root that still has the same computational properties as a Fourier transform, but isn't susceptible to round-off error. Well, the one data type that we have that doesn't have any round-off issues are integers. Integers have no notion of rounding. So what we can do is choose something that kind of, when you take a power of it, can return to 1 and doesn't have round-off error. But the thing is, integers, we can't raise them to any sort of power. If we raise, for example, 3 to the power of anything, loop for I below, I should say from 2 to 10, collect expt, I don't know, 3 to the power of I, these numbers are just growing. 9, 27, 81, they grow unboundedly. That's a problem. So how can we use integers? Well, one of the oldest tricks in the book, and one of the first things you learn in field theory, is the notion of number fields. The idea is we can grow unbounded here, but instead let's take the modulus of every number and see what the results. So let's model these by 7, for example. Well, look, we have 2, 6, 4, 5, 1. So 3 to the power of, what is this? 2, 3, 4, 5, 6. 3 to the power of 6 mod 7 equals 1. Let's increase the number. Let's do like 20 right here. And even better, we get this periodicity. We get 2, 6, 4, 5, 1. 3, 2, 6, 4, 5, 1. 3, 2, 6, 4, 5, 1. It just repeats. This is exactly like this element right here, this e to the 2 pi I. Like I said, that's going around a unit circle inside the complex plane. We're kind of, in this sense here, going through a set of integers in a repeated fashion. So the numbers mod some other number can form what we want. In a sense, this is a primitive root of unity in the field of integers modulo 7. So well, I shouldn't say this number is, let's see, this has 1, 2, 3, 4, 5, 6, 7, and then it's mod 7, so we go back to 1. So notice something else here. We're going through every single permutation of numbers. So here, let me highlight these: 1, 3, 2, 6, 4, 5, 1. So if we look at this, it just unhighlighted. We have 1, 2, 3, 4, 5, 6. In essence, computing exponents of 3 here in the field of integers mod 7 is just a permutation on those integers. We have all integers less than 7, and we go through each and every one. So that's a desirable property. So what the number theoretic transform is is the same exact thing as a normal Fourier transform over complex numbers, except that it works in this field of integers. And so that's what I've implemented here. We have to redefine our arithmetic operations. We have to do, m minus is a minus b mod m. So we have to check if a is less than b, and blah blah blah. We have all of these operations here. The hardest one, which I haven't actually solved satisfactorily right now, is doing multiplication mod m. Ideally, our multiplication doesn't go over m, and hopefully we can keep the numbers less than m, but that's not implemented right now. So anyway, we have this modular arithmetic library of functions. We can even do division. Every number has an inverse, and so we just multiply a number. Since it's a field of numbers, we just multiply a number by its field inverse here, mod m, of course, and that's what division means. So, and then with building off of that stuff, we can do exponentiation in a modular fashion and so on. So once we have that, then we can build our Fourier transforms over the field of integers. One thing you'll notice is that we'll actually need to choose a particular modulus. So if I did this same exact thing and did it mod 8, we get 1, but we get 1, 3, 1, 3, 1, 3, 1, 3. That's not really helpful. Like I said, the desirable property is that we permute through every single integer, mod 7, before we get back to 1. Here we went 1, 3, 2, 6, 4, 5. Here we're not doing everything. We're doing mod 8, but the numbers 2, 4, 5, 6, and 7 don't show up. So this isn't amenable to field computation. So what we need, with the property we need is this to be a prime. So I have all this code right here to compute prime numbers. If I do, I can actually, I can't load this, I'll load it a little later. We can compute primes, we can compute factorizations, and so on. Here's the number, the thing factorized. It's just simple division. We don't need heavy-duty factorization because we only need to do it once. But we have this code here. So for a number theoretic transform, we need to find a particular modulus. One thing, if our transform is 1 billion digits long, or 1 billion elements long, then we need our modulus to be at least 1 billion. If it's 1 trillion digits long, we need our modulus to be at least 1 trillion. The best case scenario is if our modulus is as close to the maximum representable word on our computer as possible, meaning we want a modulus, if our computer is 64 bits, to be as close as possible to, if I can type it, 64. So we want a modulus close to this, but obviously 2 to the power of 64 isn't a prime number. So I wrote this code, find suitable moduli, which will go through and find a modulus that is good. So I'm going to, before I go on here, I'm going to load all this code up into our image. So let's go into our Hypergeometrica, hypergeometrica.asd. Let's load our number theoretic transform. We also need our, what's it called? Let me look here. Yeah, our bit reversal, bit reverse. And we also want our bin split. So file, bin split as our starting. So our package is Hypergeometrica, so let's change this to NTT in package Hypergeometrica. This is still in copyright. The year is going to change soon. Let's go to our bin split.list real quick. Go up here and change this and make this 2015. This is old code from 2012. Then lastly, we need our bit reversal.